Hey, good morning. Oh, um, yes.
Do you have an
Okay.
extra problem sheet? Because I wasn't here.
Oh, they're on my course. On no, oh,
Okay.
sorry, on GitHub.
Okay, I can just do it digitally then. Is that fine?
Yes.
Okay.
Uh, okay. So let's see. Why don't I see myself? Okay. So, good morning, everybody. Few announcements. So, 2 days before break, I was contacted by two students, Gavin and Dennis. She's not here, I believe. About extension for homework submission, and I updated our syllabus, so the homework. Let's see. The homework 7, which was shifted earlier by 1 week, and the due dates fall on the break, was shifted to yesterday, like after break. And all other homeworks I shifted by 1 week also. Um, I didn't remember that I had extra week, but I had, so I could shift all the deadlines by 1 week. So, um, if I'm not mistaken, this homework, which was due to yesterday, was about a probabilistic classification. Yes? Uh-huh. Great. So, midterm, I published before, like on Friday, 1 day before break, and it's due tonight. Like last year, it was in class for 1 hour, so it shouldn't take a lot of time. I just had an extra problem, the last one that I have forgotten to include in homework about like probabilities of different models. And today, not today, this week, we actually will finish the machine learning before neural networks. So, and um, we will cover gradient boosting today and clustering next time, and we will start neural networks next week. So after this week, we will switch to deep learning. S- so yeah, do you have any questions about homework or midterm problems? If you have, just you can ask after class. So, um, if we look at the today's topic, gradient boosting or gradient boosting machine, GBM, um, I, I think this is the most important topic in the first part of the course because it's still the main algorithm for table data, for recommender systems, and um, neural networks didn't beat the performance of gradient boosting, at least for now. I think it will change in 1 year because now there are a lot of there's a lot of work on deep learning for table data, and it's the accuracy is very close to uh, model ensembles. So, and before we move forward, I just want to draw the learning curve for our course. So we started from k-nearest neighbors, which is the simplest algorithm. Just look at the neighboring points and make prediction. And then we moved to gradient descent algorithm. And I stated just the convergence property, but to understand this, it requires a lot of statistics and math. So if we draw the learning curve, then it's kind of k-nearest neighbors, then gradient descent. Then we talk a lot about metrics for classification because there are specific metrics like confusion metrics and receiver operating curve, precision and recall. It's not hard topic, but still it's something new, and maybe it was a little bit complicated. Then we talked about decision trees. Well, yeah, a little bit we talk about Bayesian classification, but just a little bit. Decision trees, I don't think it's a complicated topic. And today we will talk about combination of decision trees and gradient descent. So it's again will be a little bit kind of high level of theory, but I hope we are well prepared to understand this algorithm. And then we will move, so gradient boosting and model ensembles. And then we will go to neural networks. And I think it will be the most interesting part of the class because they're everywhere now. But we will use the built-in libraries, so I don't think it will be a hard topic and we will use gradient descent for training them. Okay, so yeah, I just want to say that if you understand gradient boosting, I will think that my mission as the teacher for machine learning class was accomplished. And you will have a homework. So next homework will be to implement gradient boosting. Of course, we will use the packages like XGBoost and LGBoost or CutBoost, but it's good to implement one model to understand better how it works. And now let's switch to gradient boosting. I updated lecture notes. I don't know, maybe I will update one more time. But now they also kind of accomplished. So yeah, I added material about model ensembles and gradient descent. Aha. But first we should finish talking about this random trees. Yep, I remember I didn't finish random trees. So decision trees. I promised you to demonstrate the code. So this is the code for problem solving from last week, like the last week before break. And in scikit-learn there is Bayesian classifier where you can indicate the size of data set, which you will want to use for individual model. You remember in one approach, we trained models on different subsets of data. If you indicate bootstrap false, then it just will take random subset without repetitions. If you indicate bootstrap true, which is by default, then it will use the data with repetition. And there is also parameter which is called OOV, OOB, I don't remember. Let's see, out of back validation. OOB, well, out of back maybe, but so let's talk about this. So as you remember, in random forest, we train individual trees, randomized trees, and as you remember, in randomized trees, we choose the features randomly, just a fixed number from a fixed number of features. So, and we build these trees on different subsets of data. So this image is not quite correct because some points will be used several times with repetition. And this image is like looks like they trained on different subsets. But for so for some point I, it was this point was won't be used in some trees. It means that we can use that trees that didn't use this point during training for evaluation, for validation. And this is called out-of-back validation. Because every model, as you remember, doesn't use about 30% of data. It means that every point won't be used at least by one tree, and we can then aggregate the trees, but only those trees that didn't use this point during training for prediction. The next thing is feature importance. There are two approaches. You did homework. If you did homework on a random forest, there is question report feature importance, and this is a built-in function in random forest because as you remember, we choose one feature for a split, and we can calculate which is called information gain or quality factor gain, like the quality in the parent node minus the quality in children. And we can sum up all these gains over all trees and over all nodes where this feature was used for splitting. And we can calculate these gains for every feature. And the feature with highest gain will be the most important feature. The other approach, which is maybe easier, to when you have features, for example, x1, x2, x, and so on, just take one column of the features and shuffle these coordinates, because our vector x is the vector of the number of features components, and then for every data point, you can just shuffle the one component and make prediction and calculate the error. The error for kind of data with a shuffled first component. Then you can shuffle the second component and calculate Y prediction and calculate the error. And what do you think, when we calculate these errors for every feature, which feature will be most important, with smaller error or with larger error?
Larger.
With larger. Because it means that if we disturb this feature, we created the greatest error. Yes, so this is what you can use in your homework for gradient boosting. There is additional task to calculate feature importance. So this is how you can implement it, but this is bonus task. Okay, so why don't we stop on this random forest model? Why do we want another model, gradient boosting? So let's just summarize the random forest pros and cons. So the main advantage of random forest is that you can use this from a box. You don't need to tune any hyperparameters. Of course, there are many hyperparameters, like the number of trees, but as this plot shows, the plot above shows the error on validation set, you can see that with increasing number of trees, we don't have increase of error, we don't have overfitting. So just, for example, take a lot of trees, like 100 trees. Maybe you need less trees, but if you take more trees, it's fine. Your algorithm won't overfit. Then the number of features which we choose to split an individual node, they are given by the paper where is it? Here. So this hyperparameter is also given. Then maybe the depth of the tree. Well, typically you would choose the depth of the tree between 5 and 10. So it's also, you can take 8, for example. So, and this model will work. Then this model has out-of-bed validation. You don't need to create validation set. But there are some also problems. So first problem is that it's slow. It's because to build all these trees to go through all thresholds, it takes time. And the other problem is that Baying also only decreases the variance, but not the biasness of the model. Do you remember we built the trees, independent models to make smaller covariance, so to decrease the variance. So let's talk about boosting idea. How it will help to decrease bias as well. So in this plot, I created one decision step for this sinusoidal waveform, and subtracted the true values and predictions, and this is the plot of errors. The idea of boosting is to build the model as a sum of models. But the second model is trained on the errors of the first model. So the second model, A2, I will fit on the difference of y minus A1. And if I sum up two models, A1 and A2, then A1 will make smaller error for the original function. A2 will decrease the error of the previous error. So after that, so the second model is trained on the errors of the first model. Then we calculate the error of these two models. So this is the difference between target and A1 plus A2. And we built we trained the third model on this error from previous two models. So you can see that now the magnitude is smaller. And when we sum up three models, the approximation will look like this. And we can continue this process. We can then calculate the errors from these three models and our data. And you can see that the magnitude of errors will decrease. Build model A4 and continue this process until we reach desired error. So this is the idea of boosting. Yes, just.
Is this different from the boosting for gradient boost? The gradient is this different from gradient boosting, or is this?
So for if we minimize MSE, then it's actually the same. If we maximize MSE loss. But now let's look at this approach for different loss functions, actually, for MSE loss and for cross entropy loss. So if we use just MSE loss, as you remember, it's just the difference squared between y and prediction. So y and prediction. Because it's the difference, we can represent, we can group these terms a little bit differently. Y minus A1 as the first term, and the second model as the second term, and it will be the same as loss between the difference between target and the first model and the second model. So it's exactly the same that I said earlier. We trained second model on the error of the first. Now let's look at the cross entropy loss. In cross entropy loss, our prediction, for example, is a class 1 or -1. If we use the same idea to train the second model on the prediction of the first model, there is a problem. If our target is 1 and prediction is -1, this difference will be 2. And 2 is not a target, it's not a label. Does it make sense? So the 2 is not it can be a target for our new model. So this is the problem. Justin asked me about the difference between gradient boosting and boosting. So this is the problem where just simple idea of boosting doesn't work. And that's why gradient boosting was proposed. Gradient boosting will work with arbitrary loss function. The idea of gradient boosting is as follows. Well, we want to build a new model. If we have k models, we want to build a model k plus 1, such that the loss function between target and our model, aggregated model, decreases smaller than the loss for the previous model when we use the sum of first k models. And I hope you remember how to decrease a function, how to find how to move our argument to make the value of function smaller. If we have the function, and let's say here we are at this point, how to choose the new model to make the value of this function smaller. For example, this is L of target is given, y is a constant. And here we have like previous model and how to choose a new model to make our loss function smaller. Let's say A plus H, for example. Do you remember how to choose this H? It falls from the name. Gradient descent. Do you remember? In gradient descent, we update our parameters. We add a negative gradient because it decreases our function. So the idea of gradient boosting to choose this H, or in other words, a new model, in the direction of anti-gradient. So we will choose the new model. We will fit a new model, not on the errors, because as we saw from the previous example with cross entropy, sometimes errors doesn't make sense, but on the anti-gradient of our loss function with some learning rate, some constant. So Do you understand the idea? Okay, now let's look at the example and algorithm, and I hope it will be more clear. And also I have some code example. Yeah, it was proposed, let's see, I have the reference in 1999, but it became more popular when it was formulated as algorithm that we built a new model on the not on the errors but on the gradient of the loss function, and it was called GBM, gradient boosting machine, because it's kind of algorithm that you can apply for arbitrary loss function. Okay, here is the algorithm. First, we choose a very simple model. For example, for regression task, you will choose the first model as average. For classification task, you can choose this model as just majority of data. Like if you have more points of class 1, just predict all the points as class 1. So choose very basic model. And on the second step, we will build, so we will calculate for every point I, we will calculate the gradient of our loss function with respect to the second argument, and calculate, evaluate this loss function at our point xi. So we will get for every point new targets as time. And we will build a new model B1 on this target. But also in this algorithm, they propose to add another constant, gamma. So after we build a new model on the gradients, we also will just do, for example, grid search. For example, just go through different values gamma between 0 and 1, for example, and choose the grammar that minimizes our loss function. And that's it. This is the algorithm. Then we built the next model, B2, on the errors, choose gamma 2, and so on. So let's look at the examples. Maybe it will be more clear. So assume we have this data, 4 points, and 6, 6, 12. Here's the data, 6, 6, 12, 18. And let's use loss function as MSE loss and quality factor as, oh, it's interesting. So the first term is SSR, the sum squared residuals that I hope you used in your midterm. But in the package which is called XGBoost, Extreme Gradient Boosting, they use extreme trees, and extreme trees include regularization term in addition to SSR. And you can see regularization term is just the sum constant times sum of squared values in our leaves. And if we minimize this function, we also will try to minimize the predictions in the leaves. So let's use this quality function to build extreme tree. So And we have some hyperparameters. In this example, I won't tune gamma, but we will use different learning rate, for example, 1 and 1/2. And let's use this lambda regularization coefficient as 1. So the first step is to calculate the gradient of our loss function. We take the derivative of this sum with respect to a of xi, and from the sum we will get just one term with index I. So it will be negative 2 times y minus module prediction, and because we use negative gradient, negative will cancel out. And also, so this is the derivative. I hope it makes sense. 2 times yi minus the first model evaluated at xi. This is just a derivative of our loss function, and then we add learning. So let's calculate this for our data. So we take y minus a, so because a is just zeros, it will be 6, and times 2, it will be 12. If we use learning rate 1/2, it will be 6. And then we calculate for second point, for the third point, and for the fourth point. So this is how we calculate the target in case of one learning rate and the other learning rate. The next step is to build a new decision step. Typically, in boosting, we use very shallow trees because what do you think? Which trees are more dependent? Deep trees or shallow trees? Yes, and we want independent models, correct. Thank you, Griffin. Yes. So to make smaller bias, we want independent models. So we use very shallow trees and typically just decision steps. So I hope now, and so we will build a new decision step, but not on target y, but on the gradients of our data. And just by observation, which threshold I should use, I think you can answer immediately if you did midterm thoughts. There I should choose the threshold x greater 1, x greater 2, or x greater 3. It's obvious. Yeah.
You should pick the threshold of x is greater than 12, I think.
Oh, well, x is greater than 2.
Oh.
Yep. Uh-huh.
Oh, wait, sorry. X greater than, yeah.
This is our target. Uh-huh.
I
Yeah, correct. So we will, of course, we should actually calculate all thresholds, all quality factors, but we know that the smaller value will be in the node with the same values. So believe me, I calculated for all thresholds. Believe me that this will be the best. So we will build a new decision stamp as follows. And now the question is to calculate the predictions. We will denote this YL and YR. Now they won't be mean because we have a different quality factor. So we should minimize quality factor. And quality looks as follows. So for the left node, we will have 2 points with predictions 12. So this is the difference 12 minus YL squared plus 12 minus YL squared, but also plus regularization term, lambda times YL squared. And now we will take the derivative with respect to YL, the prediction here. It will be 2 times this parenthesis, 2 times this parenthesis, and 2 times YL. And calculate YL from this equation. You can cancel by 2, and it will be 12 plus 12, 24, over lambda plus 2, because we have 2 YL. And if lambda is 1, it will be 24 over 3, which is, so this is how we calculate the prediction for extreme trees. Yes, so for our new model, the prediction of our model will be 8 for the left node, and for the right node, if you calculate the same, take the derivative, it will be 10. And if we calculate sorry, it will be 10 for learning rate 0.5, 20 for learning rate 1. And our new model A1 will be the sum of A0 plus B1. So our new model A1 will be the sum, and because A0 predicted only zeros, it coincides with B1. So this is B1, this is B1 for learning rate 0. Then we build the new model B2 on the gradient, and the gradient now we calculate as follows: as y6 minus the prediction of model A1. In the previous step, we used A0. 6 minus 8 will be -2 times 2. We will get the gradient -4. 12 minus 20 is -8 times 2, -6. For the other learning rate, we will use 6 minus 4, which is 2. 6, wait a second. 6, yes, 6 minus 4, which is 2. Then we multiply by 2 and multiply by 0.5. So it will be 2. Just it will be the same as the difference between 6 and 4. And build new models B2, and again by observation you can see that for the first model threshold should be x greater 2. For the model with learning rate 0.5, it should be x greater than 3. And if you calculate these parameters, you will find that the predictions for models B2, and then you should sum up A1 plus B2. And this will be the prediction for learning rate 1. This will be the prediction for learning rate 1/2. And if you compare with targets, you can see that the predictions are pretty good. Then you can build another decision tree and so on. I hope they understand the idea of gradient boosting, because you will need to implement this in home project. So when we have a model, we build a new model on these gradients. And this is the main idea. And these gradients we multiply by some hyperparameter gradient rate. Well, now we'll go to the code example, so maybe you will understand better what code. But it's important just to understand the main idea. Yeah.
I was wondering why you would get that when you're calculating the next iteration, you get the partial derivatives with respect to the predicted value. This is curious. That's it. Just for like a general formula the general algorithm stuff. We're just calculating the subsequent predicted value of this.
So for the algorithm, so here is the algorithm. So we built the sum of k models, and then we built the new model with index k plus 1. And we substitute to our gradient the value of the prediction from our current model.
Oh.
So to build a new model with index k plus 1, we take the gradient and the difference between target and our previous model, which is a sum of all these previous models. Because our goal is to build a new model to improve the prediction of the previous model.
I'm assuming the negative is just there to account for gradually going closer to the minimum.
Yes. So this is kind of combination of what we want to do earlier, the combination of gradient descent when we want optimization of it, when we want to decrease the loss function, we should move in the direction of anti-gradient. And the decision trees. Okay, let's look at the code example. So, illustration notebook. Oh, why it's not opening? Okay. This link is supposed to open directly in Colab, but maybe let's see, for example, homework. Oh no, it's not open in Colab. Okay. Yeah, I should update this link. Okay, so here's the code example. Let's run first cells with data. Because the predictions will be class labels will be 1 and 0. I converted them into 1 and -1 by subtracting 0.5 and multiplying by 2. And here's our data with class labels 1 and -1. As you remember, in logistic regression or in classification, we can use the prediction as sign of our model. Or you can use probabilities as output from logistic regression. Then threshold will be 0.5. In my case, threshold will be just 0, and plus equals 1 and negative 1. So it's important for also homework, we don't use decision tree classifier. I will use decision tree regression because I will use continuous predictions from my model. And let's build the first model, decision step. So max depth is 1. And here is our loss function. The loss function is binary cross entropy, the log of 1 plus e power negative margin, and margin is y times dot product. And calculate predictions and calculate loss for our dummy model. So this is how we built our first model. Again, you could initialize the first model just by the class 1 or class negative 1. It's the standard approach. So the next step is to calculate the next new model B1. And we calculate the gradient of our binary cross entropy. The derivative of logarithm is 1 over everything under the log. So that's why we have denominator. And then we take the derivative of this denominator and we get negative y times e as the what's called the rules for the chain rule. And then you can cancel out by e, and you will get y over 1 plus e and positive power. So I'm using this simplification in my code for the gradient. And hyperparameter eta, because you remember we should multiply gradient by learning rate eta. And finally, my new target will be negative eta times derivative. So negative learning rate times the derivative calculated between true values and the previous model. And I will train the new decision step on this target. And finally, as you remember, in main algorithm, we also had constant gamma. So now we will choose gamma 1. In my example, I use gamma as identity, and I just use the sum. But in main algorithm, we also have this parameter gamma. So I will just write the for loop. So here is y pred 1 is the prediction of my model B1. And then I just create a for loop over gamma between 0 and 1 with step 100. And choose gamma, such gamma that results in the smallest value of my loss function between, here's the formula, between target and the previous model plus gamma times the new model. So in my case, the best gamma is 1. Um, and finally, we set the new model as the previous model plus new model times this gamma. And if we calculate loss, I hope it should be smaller than for the one model. It was 0.53. This is 0.51. Yeah, so it's smaller. But it also depends on the learning rate. If I would use learning rate 0.5 or greater, then also we would move faster in the direction of the minimum of our loss function. But as you remember, in this gradient descent, there's always a possibility to overshoot. So in practice, like default parameter for learning rate is typically 0.1, just to play safe. Okay, and finally, I cast my prediction into numbers because my predictions are real numbers. You remember we used regression model. So now I use the threshold 0. So everything that was predicted greater than 0, I will classify as 1. And because it's Boolean operation, we have ones and zeros. I had classes 1 and -1. So I will cast back my classes from 1, -1 to ones and zeros. If I add 1 and divide by 2, I will get 1 and zeros. And let's calculate the accuracy. As you remember, accuracy is the number of correct guesses. So I will just take the average of the correct predictions for my model. So when my model prediction coincides with the true label. And the accuracy is 80%. So just with two models. If I build the new model, the accuracy will increase. So do you understand the idea of this algorithm? Okay, here is example of built-in models. So there are three main packages: XGBoost, extreme gradient boosting machine; LGBoost, light gradient boosting; and CutBoost for categorical data. So if for this XGBoost and LGBoost, you should apply transform like one-hot encoder for nominal data features. In CutBoost, you don't need to apply any transforms for categorical data because it will do this in very efficient way for you. So that's why it's called CutBoost. And it's still used in production, like recommender systems. So yeah, we can import this library and use dataset from California housing. So because it's not CutBoost, I should take care of the nominal column. So I create split into train and test and create one-hot encoder transform. And initialize this LGBoost regressor because we want to predict the price. Number of estimators, for example, 100. you can indicate more estimators and use early stopping when your accuracy will reach some threshold, it will just stop iterations. You can use also parameters for regularization because it's XGBoost that uses this additional regularization term. And finally, you just pass your train and validation set in this XGBoost model. And it's done. So, oh, it's a LightGBoost, sorry. Lambda is for XGBoost. So here is the score, and also these packages, they have built-in plot methods. So for example, here it plots the loss function on both validation and train data. If you remember your homework on this data set, I think the R squared score was about 0.7 maximum, maybe. But with LGBoost, it's 80%. It's 0.8. So when this algorithm was proposed and people understood this, so it was proposed in 2001, people understood this in about 2004, it became the most popular algorithm. And it is, if you know the Kaggle competition web page, so they run different competitions. So all the models from 2004 to 2000, maybe 14, all winners were, the models were gradient boosted. So the advice for you guys, if you have some table data and you need to do something with data, apply immediately this algorithm from the box. And most likely you will get the best result. We learned a lot of our models, but the first try is gradient boosting because every new model kind of improves the errors of the previous models in this gradient boosting. So it's very powerful. And also it has built-in important feature importance. So for example, to be honest, I don't know exactly, but I think here they use the Sheffield idea because it's hard to keep track of the feature importance for feature this quality factor gain. So yes, the position is the most important feature. It's the same as you get in your homework. Yeah, so this is the algorithm that you can use from the box, and it will give you most likely the best result, and for table data better than neural network, typically. So let's finish talking about model ensembles. So as you understand, one model is good, but multiple models is better. Like gradient boosting is the model ensemble. Uses boosting. We talked about bootstrap aggregation, the majority voting. There is one more model ensemble technique, which is called stacking. So the idea of stacking is very simple. If you have, for example, several models, A1, A2, A3, for example, three models, you can make predictions from one model for every point X, from the second by the second model for every point X, and use another model to make predictions. So you will get Y1 pred, Y2 pred, Y3 pred. And then, so you have true targets Yi. And then use the predictions from these models as new features, as features for another model. And you can build a new model, let's say A0, but use, instead of features X, you can use as features the outputs from previous models. So if you think about linear regression, you can build this model as, for example, a linear regression, W1, predictions from model 1, plus W2, prediction from model 2. And if your weights are 1/3, you will get just averaging. So it's kind of generalization of the averaging idea. And W3 times predictions from the third model, plus bias, for example. So if your new model is a linear regression, then this specific stacking ensembling is called blending. So blending is just stacking, but when we use a new model is a simple linear regression. So in my example below, I have trained, I believe, 2 gradient boostings and then applied linear regression over these 2 gradient boostings. So one gradient boosting, then, so this was LG-boost. Light G-boost, they used, it's called light because they use faster procedure to build decision trees. So they call this light trees, and that's why it's called light gradient boosting. XGBoost calculate predictions. So you can see that just one model, LGBoost, has accuracy R² score 0.83. And now I import linear regression and build a supermodel, but as features, I'm using the predictions from previous models. And unfortunately, the blending resulted in lower, actually, R² score than just one gradient boost. Yes?
How is the for gradient blending, how is the data picked for the final linear regression model?
So you have the table So you have a table with features x1 and targets y1, x2, y2. So you have this data set. Then you calculate predictions from the model. So it will be, for example, y1 prediction from the first model, y2 prediction from the second model. And then you use these predictions as new features. Does it make sense?
So basically, in the final model, it's going to be the linear regression will be put upon all of the data, all of the approximation.
Yeah, so for example, here I calculated predictions from LGBoost, from XGBoost, ypred1, ypred2, and I built a linear regression, but as features, I'm using predictions from LGBoost and from XGBoost. Does it make sense? Okay, I want to wrap up our topic about model ensembles, and let me show the last image. So these are different model ensembles: weighting, random forest, boosting, majority voting, blending, and stacking. Which model to use? So when we have very bad models with high bias, for example, variance, then we should choose weighting, random forest, or boosting, because even if our models are very weak, we will improve the final model with every new addition. If we have very strong models, like you saw in my code example, just XGBoost performed better than blending of two boosts. Because XGBoost is very strong model. It provides very good result. So then we can use averaging, just for example, take the average of two gradient boosting algorithms. The other problem with strong models is, like, when we will use neural networks, it takes a lot of time to train just one model. So you can use a lot of models. For decision stems, it's very easy to build hundreds of decision stems. Then you can use the model aggregation with multiple models. Okay, that's it for today. And yeah, return your midterm by tonight.